Thank you. I will talk about Cayley Snarks and Symmetric Bicirculants. This is a joint work with my PhD student Klavdija and with Dragan Milušić, who was my advisor. So at first, the definition what a snark is. A snark is a connected, bridgeless, cubic graph whose edges cannot be colored by 3 colors, so 4 colors to do that. And when we will say a non-snark during this talk, we will mean a bridgeless, cubic, 3-edge colorable graph. So 3 colors are enough to color the edges of a graph. And here is one nice example. The well-known Petersen graph is an example of snark. It's also the first known snark. Later on, lots of snarks were discovered. Here are the 2 snarks that were discovered after Petersen graph, the Planusha snarks, and now we know infinitely many snarks. But the Petersen graph is the only known snark which is vertex transitive. And before going further with snarks, we need to recall what the vertex transitive graph is. So if we have a graph, then an automorphism of the graph is a permutation of the vertex set such that it preserves the edges of the graph. And we say that the graph is vertex transitive if the group of automorphisms acts transitively on the set of vertices. And here are 2 examples. The graph on the right-hand side is vertex transitive, but the one on the left-hand side is not. To see that this graph is not vertex transitive, it's maybe the easiest way to look the complement. If you look the upper 3 vertices, in the complement, you see a triangle, and the four other vertices in the complement, it's a 4 cycle, and this is, so 3 cycle and a 4 cycle is the complement of this graph, and we clearly cannot map a vertex lying on a 3 cycle to a vertex lying on a 4 cycle. Okay, and in the title we have the Cayley graph. What is a Cayley graph? This is a special subfamily of vertex transitive graphs. It's a vertex transitive graph whose automorphism group contains a regular subgroup, meaning that there is a subgroup of automorphisms acting regularly on the set of vertices. And another possible equivalent definition of a Cayley graph is the second definition here, which is a better definition for our study of snarks. So we take a group, a finite group, and a subset of elements of this group that does not contain the identity element, such that it is inverse close, meaning that if an element is in the set S, also the group inverse element is in the set S. And then the Cayley graph is a graph whose vertices are the elements of the group and the edges are of the form. So we make a multiplication with the elements from the set S to get the edges. Okay? And it's easy to see that the Cayley graph is connected if the set S is a generating set. And here we again have two examples. Both of these 2 examples are vertex transitive, but one is Cayley graph and the other is not. So the Petersen graph is not a Cayley graph. The easiest way to see why this graph is not Cayley is to look all possible groups of order 10. We know that there are only 2 groups, and then we look for all possible generating sets of size 3, because the size of the set S tells you the valency of the graph, because you make the multiplications shown by the elements of the from the set S, and the Peterson graph is obtained. And the graph on the left-hand side is a Cayley graph on a cyclic grid. And so here is the problem that we consider. Are other Snarks amongst vertex-transitive graphs, in particular amongst Cayley graphs? And as I said before, the Peterson graph is a Snark, and it's the only known example. And this problem was considered already by Nedala and Kutnar in 2001. They proved that if there is a Cayley Snark, then there is also a Cayley Snark on a group which is almost simple. Not in the regular definition of an almost simple group, but on a group that has a small number of normal subgroups. It's written here, but it's not important to go into details. And then Primož Potočnik in 2004 considered vertex-transitive Snarks, and he proved that the Peterson graph is the only vertex-transitive Snark containing a solvable transitive subgroup of automorphisms. And in fact, this Cayley Snark problem is just a weaker form of the well-known Lova's question about existence of a Hamilton cycle in Cayley graphs. If I'm more precise, Lova's in 1969 posed a conjecture that every connected vertex-transitive graph contains a Hamilton pair. And up to now, then there are only 4 known vertex-transitive graphs without a Hamilton cycle, and all known vertex-transitive graphs contain a Hamilton pair. And why this is a special case of a Snark problem? So if we just consider cubic graphs, and we have a cubic graph that contains a Hamilton cycle, we have a full cycle which is of even length, because cubic graphs have even order, and you can color the edges on this cycle by 2 colors, and then the third color is can be used for all the remaining edges that are not lying in this Hamilton cycle. And so I'm really interested in the Hamiltonicity problem, and this Hamiltonicity problem is really hard, and then we started to consider this Snark problem, which is a weaker form in a sense, but it's still a hard problem. So here we have an example. This is the Coxeter graph. It's one of 4 known vertex-transitive graphs that do not have a Hamilton cycle. And to prove that this graph is not a Snark, it's really easy, because we can easily found a disjoint union of 2 14 cycles. So a 2-factor in a graph, and we can use 2 colors for these 14 cycles, because this graph is 28 vertices, so you cover all the vertices of the graph, and then the third color is enough for the remaining edges. And here is it's the same graph, just the graph is drawn in a distance structure, because this graph is also distance transitive. It's not important here, because I had this picture. So here the green edges is 1 14 cycle, and the blue edges is the other 14 cycle, and then the red edges. But to show that this graph is not Hamiltonian, so it does not have a Hamilton cycle, it's not so easy, so you need to consider all possibilities. And now if we go back to Cayley graphs, so if we consider this Cayley Snarks, we consider cubic graphs. And for cubic Cayley graphs, we know that the set S is of size 3, and the set S must be inverse closed. So we have 3 possibilities. how this set S looks like. And the first possibility is that all three elements in the set S are involutions. Okay? This case is really easy when searching for Snarks because we can simply color edges that corresponds to one involution with the same color and so on. We have two colors, so there are no Snarks here, but when considering homogeneity, it's still an open question. There are just some special cases where it's proven that every Cayley graph with respect to three involutions is Hamiltonian. Then the second case is that the set S has one involution and a non-involution and the inverse of this non-involution. With additional assumption that this non-involution is of even order. In this case, then it's easy to prove that there are no Snarks. Why? Because this non-involution gives you a two-vector consisting of even cycles. Because it's of even order, so you just make this multiplication as many as times as the order of axis and you get even cycles. So there are no Snarks in this type of graphs as well, and the homogeneity problem is open. And then the third type of Cayley graphs is that we have involution, non-involution of odd order, and the inverse of this non-involution. And this case is open. Because here we cannot use the simple trick, because now the element X gives you a two-vector consisting of odd sets. And then you need three colors and then another color for the edges, not line from this two-vector. And before proceeding with this third type of Cayley graphs, let me define what a TST Cayley graph is. So at first, we take a 2ST generated group. This is a group that is generated by involution, non-involution of order S, and with additional property that the order of an involution and this non-involution is of order T. Okay? And then we make a Cayley graph on this group with respect to the standard generating set, involution, non-involution, and the inverse. Okay? And when this T is equal to 3, we considered the homogeneity problem, not just a Snark problem. Okay? And there are 3 published papers. Altogether, it's about 80 pages. And with these 3 papers, the following theorem is proven. It tells us when a Cayley graph has a Hamilton cycle, and it does not solve the problem completely. There is still an open case when the group is of order 0 modulo 4 and this non-involution is of order 2 modulo 4, then our result only proves the existence of a Hamilton path but not a cycle. But since this case is such that the non-involution is of even order, we know that there are no Snarks in this case as well. And for the first 2 cases, the Hamilton cycle is the one that also is not Snarks. So it's a nice consequence, easy consequence. And what we did in our further research is the following. We generalized the method that we used here to consider the Snark problem. And I will show this an idea of this proof. So we take a 2SD Cayley graph, and we can embed this graph on a surface. We get a Cayley map such that the faces are S-gons and 2 T-gons. Okay? And then we make a quotient graph in the following way. The vertices of this quotient graph are the 2 T-gons of the original Cayley map, and we connect 2 vertices if the corresponding 2 T-gons in the Cayley map shared an edge. Okay? And it turns out that this graph that we constructed is a T-valent arc-transitive graph that admits a one regular subgroup of automorphisms. What this means? So when we said what a vertex-transitive graph is, we said that the automorphism group is acting transitively on vertices. And an arc in a graph is an ordered pair of adjacent vertices. And when the graph is arc-transitive, the automorphism group is acting transitively on the set of these arcs of the graph. And one regular means that the stabilizer of an arc is trivial. So it's a regular action on the set of arcs. And additional property of this quotient graph is the following, that the stabilizer of a vertex in here is cyclic. It's a cyclic group. It's a really nice quotient. It's a very symmetric